Okay. I'll invite questions during the talk. Hopefully that's okay.
Okay, thanks for coming. Let's go ahead and get started. Today, it's our pleasure to have Harry Levine joining us. Harry is a research scientist at AWS Center for Quantum Computing on the campus at Caltech. I've known Harry for a while. I've known him mostly in the context of his amazing work that he did with neutral atom arrays during his PhD. So he was a PhD student at Harvard in the group of Misha Lukin and collaborating with Vladan Vuletic and Marcus Greiner. They sort of reinvented neutral atom quantum computing with tweezer arrays and high fidelity Rydberg-based gates. In fact, the primary Rydberg-based quantum computing gate is named after Harry. It's the so-called LP gate, where the L is Levine. So that's actually pretty cool. He won the DAMOP Debbie-Jin Thesis Prize for that work with neutral atoms. And then a few years ago, kind of changed gears and works now on superconducting circuits, which is mostly what he's going to tell us about, specifically demonstrating dual rail erasure kind of conversion qubits. So please join me in welcoming Harry.
Okay, mics are on. Can people hear me okay? Great. I've got two mics, so hopefully it's especially good. Okay, thanks so much for the invitation to be here. It's a pleasure to talk about some of the work we're doing at the AWS Center for Quantum Computing. And in particular, what I want to talk about is already off to a rough start. Oh, there we go. Okay, so in particular, I want to talk about some efforts in the direction of trying to accelerate the path towards useful quantum computing. And when we think about where we are nowadays with the types of quantum computers people can build, there's a number of different building blocks people can take. There's superconducting circuits, trapped ions, neutral atoms. As an experimentalist, it's amazing how well controlled these systems are now, with dozens, hundreds of qubits even, gate fidelities for the hardest entangling operations below 1% error rates. This is really quite amazing, and it's progress from the last several years that has gotten us here. But when we think about where we want to be for useful quantum computing, algorithms that people think are actually going to be useful are going to require more like billions of gates to actually be successful. And so we need error rates that are not like a part in 100 or a part in 1,000, but like a part in a billion instead. So how do we get there? The general strategy, maybe I'll move over here just so I don't have to turn around. The general strategy is to adopt quantum error correction. So quantum error correction says that you redundantly encode quantum information not in one qubit, but in many qubits. And that redundancy allows you to exponentially suppress the effect of error rates. So you get that exponential suppression that can hopefully bridge the gap. Is there a mic problem? Oh, OK, no problem. Wonderful. So this redundancy allows one to exponentially suppress the effect of error rates, hopefully bridging the gap from this part in 1,000 down to the level of part in a billion. But the problem is the redundancy is very costly. One could think about typical redundancy at the level of thousands of qubits needed to encode one effective logical qubit's worth of information. So that also is very expensive, and that's what drives a lot of active area in the field of quantum error correction to try to reduce the overhead needed to encode this information. So that includes things like new forms of error correcting codes that are denser in their encoding. It also includes using more complex building blocks that are not just 2 degrees of freedom, or not just a single qubit's worth of information, but more complex modes like bosonic modes. And what I'll talk about today is a particular flavor of strategy where we say your qubit is not defined just by a fidelity. A fidelity describes the total error rate, but actually that error rate is composed of different types of physical errors that are ongoing on your system. And some of those physical errors might be more favorable than others when it comes to trying to correct them at scale. So that's the strategy I'm going to talk about. Actually, I'll say right now, please interrupt with questions at any point. So just go ahead anytime. OK, so I want to talk about one version of an error type that's actually easier to correct, and it's called an erasure error. To explain this, I want to say how it fits into the broader context of quantum error correction. So let's talk first about a standard scheme for quantum error correction based on the so-called surface code. In the surface code, you have an array of physical qubits which collectively encode one effective logical qubit. So they're entangled, they collectively encode one logical qubit. And the reasoning here, or the idea, is that these physical qubits are maybe noisy. They accumulate errors over time. As they accumulate errors, one should be able to detect those errors and correct for them before they spread too much and corrupt the logical information. Now, you're not allowed to actually check each physical qubit to see if an error occurred, because that would actually typically measure that qubit and collapse it, introducing new errors. So what you instead have to do is rely on these syndrome measurements. These syndrome measurements tell you about correlations between physical qubits in different regions of the system. And one could think about it as a very indirect form of information about whether or not errors occurred. And you get this set of indirect information, which is the syndrome result in different parts of your system. And you have to go through this process of decoding and thinking which physical errors were most likely to have given rise to this set of syndrome errors. Now, if your errors are sufficiently sparse, if you're below an effective threshold, then you can decode very effectively and you can suppress all these physical errors. So if you're below some effective threshold, if your error rate is below the threshold, then as you scale the size of the system, you get this exponential suppression in the effective logical error rate. But it is indirect information. And the erasure qubit paradigm is to say, let's assume that your qubits now have errors, but when they have errors, they'll actually raise a flag and tell you that I'm a physical qubit and I just had an error. That makes it much easier to decode. So you could think about that as having not only syndrome flags that you have to decode, but also extra flags at the level of each physical qubit. So it's easier to decode your syndrome results now. And that means that effectively, if your errors are all of this type that raise the flag, there's a higher threshold for these types of errors, rather than being the standard 1% level for random errors on qubits. This threshold goes up to about 4%. And it also allows you to correct effectively more of these errors, which means you have a higher code distance. That means not only does this fraction get 4 times smaller, but this exponent gets 2 times bigger. So you get better exponential suppression of errors as you scale your system. So that's the dream. You can use fewer qubits if your qubits only have errors that are willing to raise this flag. But most qubits they're not willing to raise this flag. And so what we're looking for is a qubit that has this property called erasure bias noise. That means the dominant type of error that occurs on it is this erasure error that raises the flag. And secondly, not only does the qubit need to raise the flag, but we need to actually be able to check that the flag was raised, extract that information without introducing any new errors into the system. OK, so what kind of qubits allow you to do this? The general paradigm is to rely on encoding your qubit in such a way that the dominant error is actually leakage out of the computational subspace. Leakage is often considered bad in quantum computing because if you don't detect it, it can actually propagate in weird ways and affect other qubits that are nearby in the system. But the idea here is to be able to detect leakage as it occurs. So there's a beautiful example that was laid out both in proposal and experiment with neutral atoms. In neutral atoms, you implement gates by exciting to these Rydberg states. And one of the dominant decay channels is for the Rydberg states to decay into other levels other than your computational states. And the beauty here is you could actually probe the fact that your atom has left the computational subspace. You could probe it without disturbing the qubit manifold. And that allows you to convert this leakage error into an erasure error where you actually know that this atom has left the computational subspace. So I want to talk about how this can help in the land of superconducting circuits. In superconducting circuits, we use a so-called dual rail encoding. This is a name that goes back to using photonic qubits, where you have a photon that can be encoded in one of 2 different possible modes. In superconducting land, we think about 2 different superconducting modes. And these modes could be microwave cavities, which is something that's being explored at Yale in quantum circuits. And we're very interested in a transmon-based encoding for dual rail qubits. So the qubit levels are left transmon has a photon or right transmon has a photon. The beauty of this encoding is that the dominant source of, or the fundamental source of errors in superconducting circuits is always photons that are leaking out of the system, T1 decay of your photons. And the beauty here now is that that takes you from your logical subspace, which is spanned by 1, 0, and 0, 1. It takes you out of that subspace into a separate level 0, 0. So the claim here will be that when the system leaves the logical subspace and goes into 0, 0, we would be able to detect that that happens, detect that this leakage occurred, which converts it into an erasure error. And that would be conversion of this fundamental source of error into the more favorable type of erasure error. I should say that if there's dephasing, if your two modes are noisy, if the 1, 0 state and the 0, 1 state have frequency noise because the modes are noisy, that will be undetected. That will not be converted to erasure errors. So it's quite important. We can get rid of the T1 decay, convert that fully to erasures. But if the modes themselves are noisy, that will persist as noise within the logical subspace. So what's very important is to find a system that's limited just by the T1 decay, where the residual dephasing is quite small. That's what motivates the use of microwave cavities as an implementation here. Microwave cavities have very long T1 times in the realm of superconducting circuits, and they have quite stable frequencies. So one could imagine that they are in this regime where they're T1 limited with very little residual dephasing. Now, we're interested in the transmon approach, and the transmon advantage is that they're compact in terms of form factor, and there's a huge amount of ongoing effort in the field to figure out how to scale up transmon processors, both in terms of designing them and fabricating them and controlling them. With quite a lot of success, I would say, in recent years, getting to the level now of many hundreds of qubits that can be controlled. The challenge with transmons is that they're not typically just T1 limited. They typically also have significant extra amount of dephasing noise. So you could imagine that you get rid of all of this T1 error by converting it to erasures, but you're left with a noisy logical subspace, 1, 0, and 0, 1. So is it possible to nonetheless use transmons by somehow suppressing this residual amount of noise in the system? So it is possible, and the way that this works, I'll see if I can move my mouse out of the way. That's not my mouse. OK, perfect. OK, so the way that this works is to use a flavor of dual rail encoding, where we take two transmons, and we park them on resonance with each other, and we design a coupling between them with some, I guess, designable strength G, like a Hamiltonian coupling between these two transmons. And the reason for doing this is that the eigenbasis, or the eigenstates of the system, this excited manifold where we encode our qubit, is now symmetrized between the two transmons. So the logical states that we actually use, the dual rail states, are the symmetric and anti-symmetric combinations of one photonic excitation in the two different transmons. So this preserves this property of T1 errors being detectable, because T1 still takes us out of the logical subspace into 0, 0. But it has this extra really important feature, which is that the eigenlevels here can be much more stable than the stability of the underlying transmons. The way to see this is imagine that one of the two transmons has some noise relative to the other. If you compute the eigenvalues of this symmetric and anti-symmetric states, they essentially add two things in quadrature. It adds the very strong coupling between them that we engineer to be pretty strong compared to the level of noise. And the level of noise is in the other direction. And so it gets quadratically suppressed when you compute the actual splitting of these levels. So you can have orders of magnitude better stability within the subspace compared with the level of frequency stability of the underlying transmons. This encoding has been demonstrated before in a beautiful experiment at MIT, showing universal single-qubit control within this manifold, and even proof of principle 2-qubit gates. But what I want to talk about is the use of this encoding as an actual erasure qubit. So talking about, first of all, how high of a coherence can we get in this subspace? Can we get really good coherence in the subspace so that we're limited just by these erasure errors that take us out of the subspace? And secondly, when the erasure errors occur, can we actually detect that they occur in real time and without introducing any new errors into the system? So that's going to be the point of the talk. I hope to show you that this is a compelling and maybe even surprisingly high coherence building block for quantum error prediction. And this is based on a recent paper on the archive. I'll point also to a related paper using the microwave cavity implementation for dual rail qubits from Yale. Okay. So I'm going to talk first in a little more detail about how we implement and operate a dual rail qubit based on these transmons. Then I'm going to talk about characterizing coherence within the logical subspace and comparing that to the rate of erasure errors. And finally, I'll talk about how well this mid-circuit erasure detection can actually work. Any questions before we jump in? Wonderful. OK, so we're using a pair of transmons to encode a single dual rail qubit. So these are two transmons that are each tunable. So they have these little squid loops, these Josephson junction loops, where we can control the amount of flux that goes through these loops and tune the transmons. So both transmons are tunable in the range of 3 to 5 or 6 gigahertz. So we can tune them and park them right on resonance with each other. And when we do, the excited manifold is a symmetric subspace that defines our qubit. So how do we run a typical experiment on this? We start by letting the system relax into 0, 0. And once it does, we apply a microwave pulse that coherently excites it from 0, 0 into the logical subspace. So that initializes the dual rail qubit in, for example, the logical 1 state. Then we do single qubit gates within this logical manifold. And we do that by taking the two transmons. Normally, they're on resonance with each other. If we modulate the frequency of one of the transmons at the energy gap of this dual rail qubit, that drives resonant rotations within the logical subspace. So that essentially could drive Rabi oscillations between these two levels. So we modulate the frequency of one of these two transmons. By controlling the phase of the modulation, we can also change the axis around which we're driving. So this gives us a universal set of single qubit gates. Typically, we'll do something like pi-half pulse with arbitrary phase control. Finally, we want to read out the logical subspace. And to do that, we take these two levels that are defining our dual rail qubit when the transmons are parked on resonance. And what we do is we adiabatically separate the two transmons so that they're no longer on resonance. And when we do that, these symmetric and anti-symmetric states adiabatically map onto pair states where exactly the left transmon has the excitation or exactly the right transmon has the excitation. And after we do that mapping, we read out both transmons. We can find out in this way if the system was in the logical 0 or the logical 1 subspace, or if the system was in a 0, 0 state. If it lost a photon, we'll see that as well. We'll see that neither transmon's excited. Or in principle, we could see that both transmons are excited, which would happen with low probability. So here's now typical data that we would get from an experiment like this. This is a Ramsey experiment on the dual rail qubit. So it's just two pi-half pulses with variable spacing in between. And we see the following information coming out of our readout. First of all, we see an exponential decay showing probability that accumulates in the 0, 0 state. So that's T1 decay from the underlying transmons, essentially indicating leakage out of the logical subspace into 0, 0. In addition to that, we see that for the information reflecting coherence within the logical subspace, we see fringes. And these fringes essentially reflect the frequency of the dual rail qubit. And we see a little bit of very small population in the 1, 1 state. OK, so that's most of the story. The other piece that we really need is the ability to detect erasure errors as they occur. And so to do that, we use another mode. We use another ancilla transmon. And the ancilla transmon is operated with a very particular goal. What we want to be able to do is interrogate the ancilla and find out if the dual rail is in the 0, 0 state, which heralds that an erasure has occurred, or that it's not in the 0, 0 state. If the dual rail is not in the 0, 0 state, we don't want to learn anything else. We don't want to learn that it was in the logical 0 or logical 1, because that would actually dephase the dual rail qubit. So we don't want to touch the dual rail qubit if it's still in the logical subspace. We only want to know, is it in 0, 0 or not 0, 0? So the way that we do that is we take an ancilla that's off-resonantly coupled to the dual rail pair. So it's dispersively coupled. And what that means is that the frequency of the ancilla depends on the state of the dual rail system. So the ancilla shows up at one particular frequency if the dual rail has decayed to 0, 0. And it shows up at another frequency if the dual rail is still in the logical subspace. The beauty of this is now we can apply a microwave pulse on the ancilla that does a conditional excitation. It only excites the ancilla if the dual rail had decayed to 0, 0. And so after this conditional excitation, we do a fast readout of the ancilla, and we get some IQ signal that comes out, standard type of readout for transmons. And this signal now tells us, were we able to conditionally excite the ancilla? If so, that means our dual rail had decayed to 0, 0, which tells us that an erasure occurred. So this is the full set of tools now. We have microwave initialization of the dual rail qubit. We can use single qubit gates within the logical subspace, read out the logical state of the dual rail, and mid-circuit erasure detection using the ancilla qubit. Here's the processor that we're using for this. It's a transmon processor. There's 3 transmons, 2 of which define the dual rail qubit, 1 of which is the ancilla. Each transmon has a capability for readout. It has charge control, which allows us to drive microwave transitions, and also flux control to tune the transmons around. For a sense of scale, the coherence times that we have here, the T1 times are at a characteristic scale of a few tens of microseconds, typically at the level of 30 microseconds or so. The phase coherence, the T2 star, is at the level of also tens of microseconds to microseconds, depending on if we're operating the transmon at a point that's flux sensitive or not. So this is the scale for coherence times of the underlying transmons. And now we'll turn to talking about what is the coherence within the logical subspace of the dual rail, separately from the rate of leakage out of the subspace. OK. In order to understand what is the coherence within this logical subspace, it's in some sense a game of post-selection. And what I mean by that is we want to say in instances, in shots or runs of the experiment where the system did not leave the logical subspace, how much phase coherence did it preserve within that subspace? So we can start with a simple example where we take an experiment like this. This is like the Ramsey experiment I showed earlier, but now it's a spin echo experiment. So again, we see the decay out of the subspace. And within that envelope, we see relatively high contrast fringes, which reflect the phase coherence within the subspace. OK, so the simplest thing you can do if you want to post-select against decay out of the subspace is to normalize these oscillations by this exponential decaying envelope. What this amounts to is post-selecting on having a final measurement of your dual-rail qubit that says that you're still in the logical subspace. So if the final measurement says you're still in the logical subspace, then you can say, how long am I preserving phase coherence only in those events? And what we see is phase coherence at the level of 100, 150 microseconds. So this is already quite a bit longer than the T1 time of the underlying transmons. But this actually is limited by something quite specific, which took a little bit of time to figure out. But this is limited by a particular effect where if you check at the end that the system is in the logical subspace, that actually doesn't mean it was in the logical subspace the whole time. It's possible that it could have left the subspace through T1 decay, and then with small probability heated back into the subspace. It turns out that this actually nicely explains why we've lost phase coherence in an approach like this already by 200 microseconds. So this really nicely explains that the system actually, with reasonably significant probability, can leave the subspace and come back. Now, this is not a fundamental problem with an approach like this. This is a problem if we only check for erasure errors at the very end of a long amount of evolution. So in order to get around this effect, and in order to actually reflect how you would integrate a qubit like this into an error-correcting code, we actually need to check more frequently than this if an erasure error has occurred to interrupt the process where an erasure error might have occurred and then it would have leaked back. And so we need to integrate mid-circuit erasure checks in order to properly get the level of coherence within the logical subspace. So here's now an upgraded coherence experiment for the dual-rail qubit. We do some kind of pulse sequence on the dual rail, like a spin echo in this example shown, pi half pulse, pi pulse, pi half pulse. And then in parallel with this measurement, we'll run a sequence of mid-circuit erasure checks. And each check will tell us if the dual-rail qubit has left the logical subspace or not. And in the end, we're going to combine all that information and post-select on all of the erasure checks saying that we stayed in the logical subspace the entire time. So here's now the measurement results for this. We have two types of information. First of all, we have the post-selection probability itself. The post-selection probability decays exponentially with time, because this should just accurately reflect the probability that the system stayed in the logical subspace for the entire time. So this decays with a characteristic timescale of around 30 microseconds, given by the underlying transmon T1s. Post-selected on having not had an erasure error, we now have much longer amounts of coherence within the logical subspace. So lots of coherence still left at around 300 microseconds. We can add a little bit more dynamical decoupling, and now we fit to a coherence time at the level of millisecond. So I should say, when we're looking at coherence at 300 microseconds, there's actually very few events where the system makes it to 300 microseconds while staying in the logical subspace. Most often it has decayed. So what we're characterizing here is in those few instances where it remained in the logical subspace, we're seeing that it actually preserved quite a lot of its phase coherence. OK, so this is T2 of the dual-rail qubit. We can also talk about T1 of the dual-rail qubit. So if we initialize in one of these two logical states, post-selected against erasures to 0, 0, how long does it stay in the logical state that we initialized? And to do this, we use a very similar type of sequence. So we initialize the dual-rail qubit in one of its two logical states. Typically, we'll initialize it into, let's say, just the logical 1 state, and then optionally apply a pi pulse to swap it to the other logical state. We hold it in that logical state for a long time, during which we do a train of mid-circuit erasure checks, and then we do our readout in the same way as before. And what we see, again, typically is if we initialize in logical 1, it stays in logical 1 with high probability out to several hundred microseconds, and same for logical 0. So we can fit a T1 time of this to about 1 millisecond. So here's one of the first ways we can compare we can define some notion of erasure noise bias. We can say, what is the rate of errors within the logical subspace, which are hopefully very small, compared to the dominant error, which is just fundamentally set by our T1, which is this 30 microseconds. So we have 30 microseconds leakage to 0, 0, millisecond scale coherence, within the logical subspace. And this defines this notion, or a first notion of this erasure noise bias. So yes, go ahead. These mid-circuit erasure checks? Okay, great question. So the question is about what is the rate at which we can do these mid-circuit erasure checks. So the mid-circuit erasure check itself takes a bit under 1 microsecond. We could, in principle, do them as rapidly as once per microsecond. What we typically find is that they actually don't need to be as close as 1 microsecond. They need to be closer or of a characteristic timescale that's set by the T1 of the underlying transmons. The key idea would be if you let the system decay into 0, 0, and you leave it there for a very long time, you start to become very sensitive to the chance that it was in 0, 0 and then heated back into the subspace, which is like a second order effect. It has to first decay and then heat back. If you check periodically at a scale set by the T1, you never let it sit for very long in the 0, 0 state. Mm-hmm. Mm-hmm. I don't think that's the case. And I think it's because the decay is like a Markovian noise process where every single time you check, there will be some small probability. As you make those checks smaller and smaller, you'll have a smaller probability, but it's all like linear. It's all exponential decay type behavior. So I don't think you could suppress this type of error by the measurement. Yeah. That's exactly right. So the question is, if you detect an erasure error, can you recover in any way, or do you stop measuring? So in practice, what we do is we run the same experiment every single time, and we just post-select on shots where the system never was flagged to have had an erasure error. That is a really critical next step, which I'll come back to, is we would need in practice to reinitialize and somehow reintegrate this dual rail qubit into an error correcting code. Yeah, I haven't shown that yet. Okay, yeah. I guess I'm not an expert, but my initial sense would be the beauty of this type of approach is we have strong nonlinearities at the level of single photons. So it's very easy to manipulate the photons. We can create new photons. We can do conditional checks on the presence of a photon. I think it's hard to achieve that without this kind of extremely strong circuit QED nonlinearity. That would be my response. Yeah. All right. Okay, so I talked about T1 within the logical subspace and T2 echo within the logical subspace. I haven't talked about T2 star. T2 star characterizes the absolute frequency stability of the dual rail qubit. And it's a slightly more complicated story. Here are now 2 example Ramsey measurements. As I said before, Ramsey measurements track the frequency of these oscillations, track the phase, or the frequency of these oscillations track the frequency of the dual rail qubit itself. These are actually 2 identical measurements taken back to back. These measurements are integrated over about a minute's worth of time. And what we find is that in some cases, we see nice clean fringes. In other cases, we see decay and revival. And this decay and revival is characteristic of some kind of noise processes on these dual rail qubits. And in particular, it's easier to understand what's going on here if we actually measure the frequency of the dual rail qubit in short time intervals. So this is integrated over about a full minute. But if we measure in second timescales, we actually see that over minute timescales, the frequency of the dual rail experiences some kind of telegraph noise. It jumps between 2 steady state levels. This is the frequency stability of the dual rail qubit itself. If we operated just one of the 2 transmons at that same operating point and moved the other transmon away, we could look at the same thing. How stable is that one underlying transmon? We find that it actually shows the exact same type of telegraph noise. In fact, these measurements are interleaved, alternating 1 point at a time. And so this time correlation here indicates that there's something in the system that causes a dispersive shift on one of the 2 transmons, or if that transmon is parked with another transmon forming the dual rail qubit, it also dispersively shifts the frequency of the dual rail qubit. This is a little bit of a puzzle because the claim is that the dual rail frequency stability should quadratically suppress the contributions of frequency noise on the underlying transmons. And so it turns out to be a little bit more complicated of a story. It turns out to come from another element in the system. Let's see, I hope this is visible enough. There's another element in the system. What we're looking at here is essentially spectroscopy of the frequency band nearby our superconducting transmons. What we find is essentially there's dark modes here. When the dark mode is present at around 5 gigahertz, it indicates that there's some mode in the system at 5 gigahertz that is coupled to our system. We find that there's some mode in the system that comes and goes. It's relatively close to tuned to our transmons. We don't exactly know what it is. When it's there, it causes a dispersive shift on the individual on one of the two transmons that comprises the dual rail. And if the dual rail is formed at this operating point, it also shifts the dual rail qubit. So it's a little bit interesting because it can't be understood as just inducing a frequency shift on one of the two transmons. Because if it just induced a frequency shift, that frequency shift would be quadratically suppressed, and it would be far too small to explain this level of noise. So it turns out to require a slightly more complex modeling for how this mode couples to the transmons. It actually requires that this mode is coupled transversely to the transmons. So this frequency shift is really a dispersive interaction, but it has to come from a transversal coupling. That's a lot of technical detail. I would claim that from a positive perspective, this is a nice tool for studying TLSs. And I think it is true that there are models for a TLS that could explain this but would not explain this. So I think it is an interesting way to probe the presence of TLSs. What's maybe more fortunate and pragmatic point of view is that this type of telegraph noise is extremely slow. It's minute scale, and we actually don't need to preserve absolute phase coherence over minutes. We just need to be able to echo out any kind of slow noise. So we're able to successfully mitigate that. Hopefully in the future, we could get rid of these modes altogether. Everybody would like that. OK. Yeah. It's just one of the two. So it's some mode that's actually physically connected to one of those two transmons. Yeah. OK, so that's talking about the coherence metrics of the dual rail qubit. Another way to characterize these types of things is to say, if we want to actually do gates on the dual rail qubit, how high fidelity are those gates? What are the error processes of those gates? So this is very similar, but now in the perspective of actually characterizing what is the error per individual gate that we're running on the system. So we characterize this with, it's all about single qubit gates. We're doing a sequence of random single qubit Clifford gates. And as with the coherence measurements, in parallel with these gates, we're doing mid-circuit erasure checks to verify that to check what is the probability that the system had an erasure per gate, or post-selected against that erasure that it had an error within the subspace. So here's now the typical data. We'll see some level of exponential decay of the survival probability of post-selection. This is now the erasure error per gate. This comes out to a little less than 0.5% per Clifford. This is set by essentially the duration of the Clifford, which is 100 nanoseconds, divided by the characteristic erasure lifetime of the dual rail qubit. Post-selected against erasures, we now have a much longer amount of survival within the logical subspace. And so this fits to a much smaller level of gate error per Clifford post-selected against erasures. These Cliffords are all composed of a pair of our atomic pi half pulses, which are the building blocks, essentially Hadamard gates. So we can also reflect this at the level of our Hadamard gates or pi half pulses. They come out to about 0.2% error per gate, or about 5 times 10 to the negative 5 residual error per gate. So this is another way of describing the effective erasure noise bias in the system. It's saying that 40 times, or there's some level of erasure errors, which is given by the underlying transmon T1s. Residual errors are about 40 times smaller than that. OK. One last point about coherence of the dual rail qubit, which is the dual rail qubit is able to passively suppress the underlying transmon frequency noise. And so with normal transmons, you don't want to operate them at So these plots, I'm showing the frequency of a transmon as a function of the flux bias applied to the transmon. Flux is always noisy. There's always flux noise in the system. So with normal transmons, you don't want to operate them at very sensitive parts of their tuning curve. But because the dual rail qubit passively suppresses frequency noise on the transmons, it actually makes it not so unreasonable to park the pair of transmons at any operating point that they can mutually access. And so we can test this by, for example, parking these transmons at various operating points. Here we're spanning about a 350 to 400 megahertz band that we're tuning over. And over this full range, the dual rail qubit preserves several hundred microseconds worth of coherence within the logical subspace. So this is an attractive capability because in most superconducting circuits, again, you typically pay a big price if you want to take advantage of tunability. You typically have to make a big sacrifice in coherence. Here, you're able to maintain quite high level of coherence while maintaining this tunability. And it's often the case that there will be modes in your system, as we see, right here. There will be modes in your system which show up in unexplained places where you don't want them. So you'd like to have that knob that allows you to just park at a different spot without paying too big a price. So the hope here is that in a large-scale processor, where now many of these qubits might suffer from kind of unwanted modes, as long as all of them have this tunability, you could hope to dodge them and improve the yield of processors in this way. OK, so that's the end of the section on coherent. Now, for the coherence measurements, I've already incorporated the idea of mid-circuit erasure checks. We actually needed the mid-circuit erasure checks in order to properly post-select on the system having never left the logical subspace. But I haven't said anything about how well these mid-circuit erasure checks work. So that's what I'll talk about in this last section. And OK, we're doing OK on time. So the mid-circuit erasure check, as a brief reminder, it consists of a conditional pi pulse on the ancilla that only excites the ancilla if the dual rail qubit has decayed to 0, 0. That conditional pi pulse plus the readout that then detects the state of the ancilla, it takes a little bit less than a microsecond. And when we think about what is the fidelity of this operation, how good is it and how good does it need to be, we have to think about several different metrics, actually, that affect this mid-circuit erasure check. So first of all, there's the possibility that the erasure check gives us the wrong result. It can give us a false positive, where the dual rail is still in the logical subspace, and it incorrectly says you had an erasure. It can give a false negative. The dual rail has decayed to 0, 0, and it doesn't correctly flag that. It can also induce extra dephasing on the system. This is a relatively invasive action. OK, it's not applied to the dual rail qubit itself, but it's applied to a coupled mode. So you might worry, we're applying microwave drive on the coupled mode. We're probing a readout resonator in the system. If those things somehow perturb the dual rail qubit, you might worry that that introduces some extra dephasing. And finally, in a real error-correcting code, you have to integrate these mid-circuit erasure checks into your rounds of syndrome measurements. And if the erasure check itself is very slow, you might worry that while we're waiting for the erasure check to complete, it will accumulate new errors into the system. So they will actually affect error performance in different ways. And I just want to give a high sense about the different ways in which these things can play a role. So to actually even understand what is the right benchmark to compare these error rates to, I'll briefly return to the idea of how this would integrate into an error-correcting code. So here's, again, the surface code. Looking in a little bit more detail, syndrome measurements, which are repeated at a rapid, as fast a cycle rate as you can in an error-correcting code, they consist of the following type of measurement. So you have an ancilla qubit. This is not the ancilla we're using to detect erasure errors. I should probably use a different term there. This is now one of the physical qubits that actually sits at the center of this square and is used to detect the correlation in the state of the qubits around this square. So we have an ancilla qubit of that style. And in order to extract the syndrome results, we do these conditional NOT gates between the data qubits and the ancilla qubits. And then we measure the state of the ancilla qubit. In an erasure-enhanced surface code, what we envision is adding erasure checks essentially alongside every single 2-qubit gate, so that we find out for each 2-qubit gate, did it fail because we had an erasure flag. So if you implement a scheme like this, then the errors induced by the erasure checks will essentially add to the errors of the 2-qubit gates themselves. And so to understand how good these erasure checks need to be, we have to compare to how good do the 2-qubit gates need to be themselves. So here's now a plot. This might be hard to read. This is a plot that shows the threshold of a surface code with a combination of erasure errors and residual Pauli errors that are undetected. This is the relevant line here that shows the boundary of this threshold. So if you have no Pauli errors, if you have only erasure errors, you can tolerate up to about 4 or 5%. If you have no erasure errors and only Pauli errors, you can tolerate up to about 0.7%. So we'll set as a benchmark some point that's relatively deep below threshold that consists of about 1% erasure error, which is well below the 4% threshold, and about 0.1% Pauli error. So this will be a rough guideline. I mean, the numbers here would need to be, would be studied in more detail at a later point. But this is a rough guideline for what errors we would like. So now we need to think about the different error mechanisms of these erasure checks and how do they fit into this category of either erasure error that's induced on the system or residual Pauli error. So as an example, we can think about false positives and false negatives. So false positive we characterize by initializing the dual rail in the logical subspace, doing an erasure check. Hopefully the erasure check always tells us that there was no erasure error. But with small probability, it does tell us that there was an erasure. That's an incorrect false positive. This averages out to about 0.6 to 0.8% averaged over all the different logical states of the dual rail qubit. So this essentially injects extra erasure errors into the system. Because it tells us that there's an erasure error, we have to assume that it's correct. So it injects new erasure errors. It's a little bit below this target level, but still could use some improvement. False negatives, similarly, we initialize the dual rail qubit in the 0-0 state, where it should flag that an erasure error occurred. Most of the time, it does flag erasure, but with small probability, it says that there was no erasure. When we think about this in an error correcting code, what actually matters is the probability both that an erasure occurred and that we missed it. And that's actually the product of two relatively small probabilities. First, the probability that an erasure occurred in a single round in a small unit of time. And then if it occurred, did we miss it? So this could be bad. If you miss the presence of an erasure, it could propagate in later rounds as Pauli errors. It could propagate in undetected ways. So this should be pretty small, but it already is relatively easy to achieve a pretty small level of effective error rate here. Maybe the more interesting one is, does the act of checking for an erasure induce additional dephasing on the dual rail qubit? And to characterize this, we do a spin echo measurement on the dual rail, but we fix the duration time of the spin echo. So the dual rail should have some amount of phase coherence left after this duration. And now we'll insert more and more erasure checks and see if adding more erasure checks causes extra dephasing. So there's a little bit of a funny result here, which is that as we go from 0 erasure checks to a small number, it actually looks like we're improving the coherence of the dual rail qubit. This comes back to the original idea that if we don't do any erasure checks, then the coherence at this point appears to be limited by the probability that the system might have had an erasure and then come back into the logical subspace. If we add a few erasure checks, we start to interrupt that process. We do the post-selection like we've been doing in most of the coherence measurements that I've discussed. And that actually boosts the apparent coherence to a more accurate reflection of how much coherence is left if we actually stayed in the logical subspace the whole time. So that reaches some plateau. And now one would wonder, does that plateau continue with some exponential decay as you add more and more erasure checks? And there's a relatively small amount of residual decay as we do more and more checks, bounded pretty conservatively at the level of about 0.1%. So consistent with this target level that we've set as a benchmark. So here's a rough recap. There's some level of injecting erasure errors with false positives. There's a chance that you miss true erasure errors. There's some potential for dephasing as you do more and more checks. And finally, the idling coherence error is actually probably the one we have to work on the most. Right now, the erasure check takes just under a microsecond. During that time, there's actually a non-trivial chance to have a new erasure error. That's not so good. So this is probably the one we need to work on the most. But we're already approaching the targets that we would be needing to actually integrate into an error correcting code. And I would say this is really a first version of all of these of this type of erasure check. And so there's many opportunities to both speed it up and do this kind of thing with higher fidelity. So that brings me to some of the next steps here. First of all, as was mentioned already in a comment, after you flag an erasure error, what you really need to do is reinitialize the dual rail qubit so that you can integrate it into another round of syndrome measurements. When you reinitialize the dual rail qubit, it essentially is in a random state, and it's unconnected to it's not entangled with the rest of the system. So you need to do new syndrome measurements on that dual rail qubit to stitch it back into the surface code. We also are thinking that a better form of erasure detection that would be both faster, higher fidelity, and more compact would be, instead of using an ancilla qubit, we could actually just have a single resonator that's coupled to both transmons. And by probing this resonator, we could immediately check if there's exactly one photon in the system shared by these two transmons. So we're thinking that might be a more effective strategy going forward. And finally, if we're really going to integrate this into a surface code, we need to be able to entangle two dual rail qubits. That's the building block for syndrome measurements and error correction. And the hope would be that these 2-qubit gates would also be primarily limited just by erasure errors during the gate, rather than any residual dephasing or decoherence that's undetected. So hopefully this, we see this as an exciting path towards hardware efficient error correction, where we can use fewer ultimate qubits and resources in our processor to achieve the same level of logical error rates in the system. So I want to thank the team at AWS. This is our building. We're on the corner of Caltech campus. And thank you so much for your attention.
All right. Thanks, Harry, for a great talk. Any other questions for Harry? Yeah.
Yeah. So in terms of increasing the coherence of the qubit, the main thing that hurts us during the idling error is erasure errors. And that's because while we're idling, the main thing that hurts us is erasures. We would like to increase or decrease the erasure error rate. That just means increasing transmon T1. So we want to increase transmon T1. It makes everything better here. But assuming you have some level of T1 you're able to achieve, the other thing you can do is try to make these erasure checks faster. Using the ancilla approach, there's already a little bit of room. So it consists of these two things: the microwave pulse that is conditionally exciting the ancilla. That has to actually be a little bit slow. It's a half microsecond. And the reason it's so slow is that we need to be able to resolve the two transition frequencies of the ancilla. It's either here if the dual rail is in 0, 0, or it's only a bit less than 2 megahertz away if the dual rail is still in the logical subspace. So that defines how slow this microwave pulse needs to be. We could engineer higher dispersive coupling so that there's a larger gap there and do faster microwave pulses. So we could probably get a couple hundred nanoseconds less there. The readout of the ancilla is about 300 nanoseconds right now. There's certainly some room to improve there. But probably this new approach where we just take one resonator coupled to both transmons, that might be the most effective way to do faster erasure checks. There's another question here.
Yes.
Yeah. They do. They have individual flux lines.
So what do that?
That's a good question. It needs to be adiabatic, but it needs to be adiabatic with respect to the energy gap of the dual rail qubit. I think I had it written, but I didn't say it. That energy gap for these qubits was 180 megahertz. That's a pretty big energy gap, so it doesn't even need to be that slow to be adiabatic. So I think tens of nanoseconds ramp apart of the dual rail qubit is already enough to be adiabatic. So the thermal population of these transmons is a couple tenths of a %. I don't think we have any evidence to contradict that, but maybe it would be hard to. Yeah. I see. Yeah, so I don't think that energy gap is the right thing to think about with thermal population. I would think about it as the transmons have some rate of leaking photons from the system and some rate of photons entering the system at the 5 gigahertz band or so. You park them on resonance, but it still is the same consideration. There's going to be a rate of leakage, a rate of photons entering the system. So it ends up coming about to the same thermal population. Yeah.
Yeah.
Yeah. Yeah. Yeah.
How good can they get?
That's a really good question. So I would say we want the qubits to be, the physical transmons should be as good as they can be. If there's ever a reason why we should make the transmons worse to make this approach better, then this approach should be scrapped. Like I would, that's very clear. What I would claim is that if the transmon T1, I'll say it in the following way. We're like 10 times below state-of-the-art transmon T1s. State-of-the-art transmon T1s are a few hundred microseconds. But the coherence within the logical subspace, right now it's about a millisecond. We think it could be many milliseconds. We think we're not close to the limit there. And so even if we are able to hit hundreds of microseconds T1, it still is going to be the dominant source of error relative to what we think should be possible at the level of many milliseconds within the subspace. So it does change it changes the arithmetic a little bit, because you then have to think differently about what limits the coherence within the logical subspace compared to what limits coherence of underlying transmons. And it is limited by different things. For example, the dual rail qubit, the coherence within the logical subspace is limited by flux noise at that energy gap, flux noise at about 200 megahertz. Transmons are typically not limited by that flux noise. And so, in principle, one could have a world in which that is harder to address than the noise on the underlying transmons. But I think in practice, that's actually going to be an easier problem to solve. So we should be able to get quite long coherence times within that logical subspace. And hopefully everybody wins by improving transmon T1s and coherence. Well, we haven't done 2-qubit gates yet. Yeah, so numerical simulations incorporating the levels of noise that we have here are pretty optimistic in terms of what they indicate should be achievable. So the erasure error per 2-qubit gate, that's fixed. That's going to be set by how long is a 2-qubit gate divided by the transmon T1 time. The residual error rate, that's the big question. How low can we get that? The level of noise on the logical subspace is small enough that that's going to be, a very favorable small residual error rate if you take a naive calculation and say, we have millisecond-scale coherence within the logical subspace. The 2-qubit gate should be 100 nanoseconds. So that would say 10 to the minus 4 residual error within the logical subspace. I would love if that's, possible to achieve. It's very possible that other technical issues would become limiting. So that remains to be seen. That's the big question.
Okay, any final questions?